Imagine being able to monitor millions of farms without setting foot in a single field. In 2026, that's exactly what's happening across India's Kharif season. Using satellites, artificial intelligence, and GIS, scientists can track crop health, detect drought stress, estimate soil moisture, and even predict harvest yields from space. These powerful technologies help governments respond faster to floods and droughts, support crop insurance, and enable smarter farming decisions. So, how do satellites actually see crops from hundreds of kilometers above Earth? Let's explore the fascinating science behind India's space-powered agriculture revolution. Before we explore satellite technology, let's understand what Kharif crops are. Kharif crops are planted at the beginning of the southwest monsoon, usually between June and July when rainfall provides the water needed for healthy growth. These crops are then harvested in autumn from September to October, depending on the region and weather conditions. India's major Kharif crops include rice, cotton, soybean, maize, groundnut, millets, and sugarcane. Together, they play a vital role in the country's food security, economy, and agricultural exports. Because their growth depends heavily on rainfall and weather conditions, accurately monitoring these crops throughout the season is essential. And that's where satellites, AI, and GIS make a remarkable difference. To monitor India's vast Kharif crop fields, scientists rely on a combination of Indian and international Earth observation satellites. Each satellite has unique capabilities, and together they provide a complete picture of crop conditions throughout the growing season. Let's begin with ISRO's Resourcesat series. These satellites are specifically designed for natural resource monitoring. They capture multispectral images that help estimate crop acreage, monitor vegetation health, and assess agricultural conditions across large regions. Resources at data has become one of the key sources for agricultural planning in India. Next is Cartosat. While Cartosat is best known for producing high-resolution images for mapping, it is also extremely useful in agriculture. Its detailed imagery helps identify field boundaries, irrigation networks, and land use patterns, making it valuable for precision farming and crop management. Another important group is ISRO's Earth Observation, or EOS, satellites. These modern satellites carry advanced sensors that collect information on vegetation, land cover, water resources, and environmental conditions. They support continuous monitoring of crops and help improve agricultural decision-making. India also uses data from international satellite missions. One of the most important is Sentinel-1, developed by the European Space Agency. Sentinel-1 uses synthetic aperture radar, or SAR, instead of a traditional camera. Unlike optical satellites, radar satellites actively send microwave signals toward Earth's surface and measure the reflected signals. Because microwaves can penetrate clouds, rain, and haze, Sentinel-1 can capture images even during heavy monsoon conditions, making it one of the most reliable satellites for Kharif crop monitoring. Another valuable mission is Sentinel-2, which uses optical sensors. It captures high-resolution images in multiple spectral bands, allowing scientists to analyze crop health, vegetation growth, and calculate important indices such as NDVI. However, because it depends on sunlight, thick cloud cover during the monsoon can sometimes limit its observations. The Landsat 8 and Landsat 9 satellites operated by the United States also play an important role. They have been providing consistent Earth observation data for decades, making them excellent for studying long-term agricultural trends, land use changes, and seasonal crop development. So what's the difference between optical and radar imagery? Optical satellites work much like a digital camera. They capture reflected sunlight, producing natural-looking images that reveal crop color, vegetation health, and land cover. These images are highly detailed but cannot see through clouds. Radar satellites, on the other hand, generate their own microwave signals. Since they don't rely on sunlight, they can operate both day and night. More importantly, these microwave signals pass through clouds and rain, allowing scientists to monitor fields even during the peak monsoon season. By combining optical imagery for detailed vegetation analysis with radar imagery for all-weather monitoring, Scientists can continuously track crop growth, detect flood damage, estimate soil moisture, and produce more accurate crop forecasts. Together, these satellite systems form the backbone of India's modern agricultural monitoring program, helping farmers, researchers, and policymakers make faster and more informed decisions. So, what exactly do satellites measure to monitor crops from space? They collect far more than just pictures. They capture scientific data that helps experts understand what's happening in every field. One of the most important measurements is NDVI, or the Normalized Difference Vegetation Index. NDVI measures how green and healthy crops are by analyzing the light reflected from plants. Higher NDVI values usually indicate healthy, actively growing vegetation. Another useful index is EVE, or the Enhanced Vegetation Index. It provides even more accurate information in areas with dense vegetation, making it especially useful for monitoring crops during peak growth. Satellites also estimate soil moisture, helping farmers understand whether fields have enough water or are beginning to experience drought stress. They measure crop acreage to estimate how much land is planted with different crops, which is essential for forecasting production. During extreme weather, satellites perform flood mapping, quickly identifying flooded agricultural areas so governments can respond faster and assess crop damage. They continuously monitor vegetation health, detecting signs of stress caused by drought, pests, diseases, or nutrient deficiencies before they become visible to the human eye. In addition, satellites measure land surface temperature, helping identify heat stress that can reduce crop productivity. They also generate rainfall estimates by combining satellite observations with weather data, allowing scientists to monitor rainfall distribution across large regions. Together, these data sets provide a real-time picture of India's agricultural landscape, enabling more accurate crop monitoring, better yield predictions, and smarter farming decisions throughout the Kharif season. Collecting satellite data is only the first step. The real magic happens when artificial intelligence, or AI, analyzes that data to uncover patterns that humans might miss. First, ASI can identify different crop types by recognizing unique patterns in satellite images. It can distinguish rice, maize, cotton, soybean, and other crops across millions of hectares with remarkable accuracy. AI also detects crop stress at an early stage. By analyzing changes in vegetation, soil moisture, and temperature, it can identify fields affected by drought, heat, or nutrient deficiencies long before the damage becomes visible. Another important application is yield prediction. AI combines satellite imagery with weather records, soil information, and historical crop data to estimate how much farmers are likely to harvest months before the actual harvest. AI can also detect disease risks by spotting unusual changes in crop growth patterns. This helps farmers take preventive action before diseases spread across large areas. At a larger scale, AI estimates total crop production for districts, states, and even the entire country, helping governments plan food supplies and market policies. Finally, AI generates early warnings for droughts, floods, pest outbreaks, and extreme weather, allowing faster responses that reduce crop losses. In simple terms, machine learning is like teaching a computer using thousands of examples. The more data it learns from, the better it becomes at making predictions. Deep learning is a more advanced form of machine learning that uses artificial neural networks to recognize complex patterns in massive satellite datasets, making modern agricultural monitoring faster, smarter, and more accurate than ever before. Satellite images and AI are powerful on their own, but Geographic Information Systems, or GIS, bring everything together on a single map. Think of GIS as the digital platform that combines multiple layers of information to provide a complete picture of what's happening across agricultural landscapes. GIS integrates satellite imagery, weather data, soil maps, village boundaries, and irrigation networks into one system. By combining these different data sets, scientists can analyze not just how crops look, but also why they are growing well or struggling in a particular location. The result is a range of powerful maps and decision-making tools. GIS creates crop health maps that show where crops are thriving and where they need attention. It also generates drought maps, helping identify areas experiencing water stress before serious damage occurs. During extreme weather events, GIS produces flood impact assessments by overlaying satellite images with village boundaries and farmland locations. This allows authorities to quickly estimate crop losses, identify affected communities, and prioritize relief effort. Perhaps most importantly, GIS provides decision support for governments. It helps policymakers plan irrigation projects, allocate agricultural resources, monitor food production, respond to disasters, and design better farming policies based on accurate location-specific information. By combining satellite data, AI, and GIS, India is building a smarter agricultural monitoring system that enables faster decisions, improves crop management, and strengthens food security for millions of farmers. The greatest impact of satellite technology, AI, and GIS is seen where it matters most, on the farm. These technologies provide farmers with timely information that helps them make better decisions and reduce crop losses. One of the biggest advantages is early drought alerts. By monitoring rainfall, soil moisture, and vegetation health from space, scientists can detect water stress before crops begin to wilt. This gives farmers valuable time to adjust irrigation or adopt water-saving practices. Satellite data also supports better irrigation planning. Instead of watering fields on a fixed schedule, farmers can apply water where and when it is needed, saving both water and energy while improving crop productivity. Another important benefit is crop insurance verification. Satellite images provide objective evidence of crop conditions before and after natural disasters, making insurance claim assessments faster, more accurate, and more transparent. During floods, cyclones, or droughts, satellite-based monitoring enables faster disaster assessment. Authorities can quickly identify affected areas and deliver relief, compensation, and recovery support to farmers without unnecessary delays. At a national level, accurate crop monitoring contributes to improved food security by helping governments estimate production, manage food supplies, and prepare for potential shortages. Finally, these technologies support better policy decisions. Reliable agricultural data helps governments design effective farming programs, improve irrigation infrastructure, and allocate resources where they are needed most. Together, satellites, AI, and GIS are transforming agriculture from reactive to proactive, helping farmers reduce risks, increase productivity, and build a more resilient future. Although satellite technology has transformed agriculture, it still faces several challenges. During the monsoon, cloud cover can block optical satellite images, making regular monitoring difficult. Some satellites also have limited image resolution, which makes it harder to analyze India's many small and fragmented farms. Processing the enormous volume of satellite data requires powerful computers and advanced AI algorithms. In addition, satellite observations must be validated through ground verification to ensure accuracy. Despite these challenges, continuous improvements in radar technology, AI, and higher resolution satellites are making crop monitoring more reliable and effective every year. The future of agriculture is becoming smarter, faster, and more connected. AI-powered digital farming will combine real-time satellite monitoring, drones, and IoT sensors to track crop conditions around the clock. Precision agriculture will help farmers apply the right amount of water, fertilizer, and pesticides exactly where they're needed, reducing costs and protecting the environment. Looking ahead, digital twins or virtual models of farms could simulate different farming scenarios before decisions are made. Follow AgriTech Explained for more videos on AI, GIS, remote sensing, drones, and the future of smart agriculture.